The last thing that I proved in the previous lecture was a first part of a first criterion of integrability, which was stated in the following way, that if there always exists a partition for any epsilon, there exists a partition p epsilon, such that the difference between upper Darboux sum of f and lower Darboux sum f of f over that partition, if that is less than epsilon, if for each epsilon can find such a partition, then it automatically means that my function is Darboux integrable. Again, in our overestimation and underestimation language, this means that I can find the partition such that overestimation over that partition minus underestimation of that partition I can make arbitrarily small. So that means that eventually I should be able to make overestimations equal to underestimations. So that means that I'm able to compute the area under the graph. So we also have the opposite statement, which also is a part of the first criterion of integrability. And so the opposite statement says that suppose now that f is integrable on AB. Right, and remember that, as usual, f is a bounded function on AB. Then for every epsilon greater than 0, there exists a partition p epsilon of AB such that u of fp epsilon minus L of fp epsilon, this quantity is less than epsilon. So let's prove this. So suppose that f is integrable on AB. Then in this case, then u of f, which, as you might recall, is equal to the infimum over all possible partitions of u of fp, of upper Darboux sums, then this is equal to L of f, the lower Darboux integral, which is the supremum over all possible partitions of L of fp. Okay, so if this is the case, then if I fix some epsilon greater than 0, then let's use the first statement first. What does it mean that the infimum of u of fp's is equal to u of f? That means that I should be able to find u of fp arbitrarily close to u of f and greater than u of f, right? So that means that then there exists a partition P1 of AB such that if I increase U of f by any amount, right? If I increase the infimum by any amount, so that means that I should be able to find U of fp, which is less than that slightly increased U of f, right? It's the same property of the infimum that we have been using forever now. So in this case, I'm going to increase U of f by epsilon over 2, so such that U of fp1 is going to be less than U of f plus epsilon over 2. Right, again, this is the statement that holds due to the fact that U of f is an infimum of U of fp's. And because L of f is a supremum of L of fp's, that means that if I lower L of f by epsilon over 2, I should be able to find L of fp, which is larger than L of f minus epsilon over 2. So, and there exists a partition P2 such that L of f minus epsilon over 2, right? So if I lower my supremum by some small amount, I should be able to find an element of the set over which I am taking a supremum, which will be larger than this. So this is greater than L of f P2. All right. Okay, so if we agree on this, then if I set P epsilon to be the union of P1 and P2, P epsilon is a refinement of both P1 and P2, right? So P epsilon is a partition of the interval AB, and it's a refinement of both P1 and P2 because it contains both P1 and P2, and it has more points than either one of those. Okay, and so in that case, by the refinement theorem that we proved before, if I'm refining a partition, that means that I'm lowering the upper Darboux sum and I'm increasing lower Darboux sum. So therefore, from this, I can conclude that U of f P epsilon must be less or equal than U of f, and in this case, I'm just going to compare to P1. And right, because P epsilon is a refinement of P1. And L of fp epsilon is greater or equal than L of fp2, because again, P epsilon the refinement of now P2. All right, and from this now I can, so this is not really an implication. But now we're going to get an implication of the above statements. So first, I know that U of fp1 is less than U of f plus epsilon over 2. And on the other hand, I know that U of f p epsilon is less or equal than U of f p1. So from this, by combining this statement with this statement, I see that u of f p epsilon must be less than u of f plus epsilon over 2. So u of f p epsilon is less than u of f plus epsilon over 2. And I have a similar statement for L of f, right? L of f minus epsilon over 2 is less than L of f p2, but L of f p2 in turn is less than L of f p epsilon. So combining this inequality with that inequality, we get that L of f, actually let me write it in the opposite way, we get that L of f p epsilon is going to be larger than L of f minus epsilon over 2. Well, but from L of f being less, L of f p epsilon being greater than L of f minus epsilon over 2, so then if I multiply this by minus 1, I will get that minus L of f p epsilon is going to be less, I have to switch the sign, minus L of f plus epsilon over 2. And then if I add two inequalities, this one and that one, I see that u of f p epsilon minus L of f p epsilon is less than u of f minus L of f plus epsilon over 2 and plus another epsilon over 2. So plus epsilon. But in this case, again, the function was integrable on AB, so u of f is the same as L of f. So really, it follows that u of f p epsilon minus L of f p epsilon, that this is less than epsilon, right? And that's exactly what we try to show. Again, if the function is integrable, these two guys are the same, and so u of f minus L of f is 0, and epsilon is the only thing that would remain. And so the opposite of the first criterion of integrability is true. So in fact, I can now state the first criterion of integrability in the following way. So let's make this number 8. This statement basically becomes if and only if statement. So from 6 and 7, suppose that for, okay, so let me fix this up. So f is therefore integrable on AB. If and only if for any epsilon greater than 0, there exists a partition for which a difference between upper and lower Darboux sums is going to be less than epsilon. And that's our first criterion of integrability. Okay, so if there is a first criterion of integrability, then of course there should be more. And I'm going to prove the second criterion or Cauchy criterion in a moment. But before doing this, let me prove the following statement. Well, actually, let's try to look at this first. Suppose that P and Q are partitions of AB. Such that Q has one more point than P. And let's suppose that then these two partitions look like this. P is, as usual, A equal to x0 less than x1 less than etc. less than xk less than xk plus 1 less than etc. less than xn equal to b. And Q will have one more point that lies between xk and xk plus 1. So Q is A equal to x0 less than x1 less than etc. less than xk less than let's call this x bar less than xk plus 1 less etc. less than xn equal to b. Okay, so let's suppose that I have two partitions like that. So then we know so we already showed that for any bounding function on the interval AB, I have u of f p, which is, right, if I'm refining, u goes down, so this would be greater or equal than u of fq, and again, if I'm refining, the lower Darboux sums go up, so L of fp is going to be less or equal than L of fq. And from this, actually, by multiplying the second inequality by -1, and adding it to the first equation, what I get is that u of fp minus L of fp right, because if I multiply the second equation by -1, I get that minus L of fp is greater or equal than minus L of fq, and if I take that equation and I add it to this one, I will get the equation that I am just trying to write, that this is greater or equal than u of fq minus L of fq. Right, so the difference between upper and lower Darboux sums for a given partition is going to go down when this partition is refined. Right, so that is something that we already showed. What I want to do, I want to estimate by how much this decrease, how large this decrease can be. So I want to estimate and this is going to be important in what we're going to do next. So I know that this guy is strictly bigger, or not strictly bigger, but bigger than this guy. And by the way, one more thing that we know is that upper Darboux sum minus lower Darboux sum is always going to be positive, right? In fact, for any upper Darboux sum and any lower Darboux sum. So let me just add that here. So this thing is greater or equal than 0. So what I want to do, I want to estimate the difference between the two differences. So this guy minus the one which is smaller. Okay, so estimate how large this can be. Well, let's see. For that, we need to remember what exactly u of fp minus L of fp or u of fq minus L of fq, what is this? In fact, yeah, let me write this down. So we have u of fp minus L of fp. What is that? This is a sum k from 1 to, actually let's use I from 1 to n of capital M of f x I minus 1 to xi times xi minus xi minus 1, right? That's upper Darboux sum. Minus a similar sum, but using little m, the infimum. So just replace big M by little m. So notice that both sums have exactly the same number of elements. And the only difference between these two terms is big M and little m. So I can combine two sums into one, and it will look as follows. Sum I from 1 to n. And then we have big M minus little m, right? Because this is, after I combine the sum, there's a common factor of xi minus 1. So minus little m and the common factor is xi minus 1. Okay, that's for P. And for Q, things actually should going to look very similar. Very similar in what way? I need to make some adjustments here. What's the difference between P and Q? For Q, I have one extra point between xk and xk minus 1. Now, outside of the interval from xk, one extra point between xk and xk plus 1. So outside of the interval from xk to xk plus 1, P and Q look exactly the same. And so what I should see exactly the same sum if I is not equal to k plus 1, right? Because on the interval from k plus 1 from k to k plus 1, I'll see something different. But before k and after k plus 1, the sums are going to look exactly the same. So u of f p, well, u of fq minus L of fq, so that is going to be equal to u fq minus L of fq. That is exactly the same sum as I see here. Except that similar terms are going to be seen on the interval from 1 to k, right? Right, because two partitions on all subintervals from 1 to k minus 1 look exactly the same. And they also look the same on all subintervals starting from k plus 1. So on the interval from k to k plus 1, things are different, but then from k plus 1 to n, they look exactly the same. So plus the same sum, except that now we're going from k plus 1, k plus 2 to n. So the only interval that I'm not accounting for is an interval from k to k plus 1 again. And in fact, for q over this interval, so for p we had one interval xk plus 1. For q we have two intervals. One is from xk to x bar, and the second interval is from x bar to xk plus 1. So those I'll have to now write down separately, include separately. So what else we're going to get? We're going to get plus m. But the terms themselves look exactly the same, right? They're going to be capital M on an interval minus little m on the same interval times xi minus 1. So we have capital M on the interval from xk to x bar. So f xk x bar times x bar minus xk minus little m of the same thing. Actually, let me modify this. So minus little m of fxk x bar supremum minus infimum, and this should multiply the length of the interval from xk to x bar. Right, I'm basically adding the same terms, capital M minus little m, the difference times the length of the interval, right? Because there is stuff that comes from upper Darboux sum minus the stuff comes from the lower Darboux sum. And that's that. So that's on the interval from xk to x bar, and then there is a second interval from x bar to xk plus 1. So I can just copy again and adjust. So the next interval is from x bar to xk plus 1. And so this is an interval from x bar to xk plus 1. And then the difference is between xk plus 1 and x bar. Okay, so that's my u of fq. And so now what I'm going to do, I said that I want to figure out how large is this difference. So let's copy that. So what is this difference? That's u of fp minus L of fp, which is this sum here. So let me copy it. Sorry. So this is u of fp minus L of fp, and from that we have to subtract the corresponding quantity for u of fq minus L of fq. So this is minus. I'm going to put the bracket like this, minus this, and all of this junk is contained in the bracket that I'm subtracting. It's a lot of stuff, but actually you'll see in a moment that most of it, in fact, will cancel out. Okay, so let's look at this sum here. This is the sum of guys from 1 to n. And then I'm subtracting from it the sum of similar things, but that sum is from 1 to k. So that means that all terms from 1 to k in the first sum I can cancel out, because the circled thing and first k terms in this sum are identical. So I can get rid of the first k terms. Then if I look at the part of a sum from k plus 2 to n up here, right, all of those terms again are in the first sum up here, so they will also cancel out. So from I to k and from k plus 2 to n, all terms are gone. And so the only term that survives then is a term from corresponding to k plus 1, right? Because from I to k, I can get rid of. From k plus 2 to n, I can get rid of. So the only term that I'm not getting rid of is the one from k corresponding to k plus 1. And so from the circled sum, the only term that survives then is the k plus first term. So this is capital M of f xk plus 1 minus lit lem of f xk xk plus 1. And this whole thing is multiplied by the length of the interval xk plus 1 minus xk. All right, and in the second, this large sum of sums in the brackets, right? So now I got rid of this guy, I got rid of this guy, and so the only things that remain are these two terms that I wrote separately. And so let's copy them. And I was subtracting them, so that means that I have to replace plus sign in front of them by the minus sign. So minus and minus. There's a lot of notation here, a lot of terms, and this thing looks pretty ugly, but actually it's not that complicated, as I hope you will see in a moment. Okay, so now what am I doing here? I'm multiplying this difference by x bar minus xk, and I'm multiplying that difference by xk plus 1 minus x bar. Well, so what does that mean? That means that actually if I add xk, if I add these lengths of two intervals, x bar minus xk plus xk plus 1 minus x bar goes away, and I just have xk plus 1 minus xk, right? Which should be obvious, right? Because what is x bar? X bar is a point that subdivides an interval from xk to xk plus 1 into two smaller subintervals. And so what I'm going to do is I'm going to replace then xk plus 1 minus xk here by the following expression, basically by adding and subtracting x bar. I have minus x bar plus x bar minus xk. And so then if I open the parentheses, then I get the following thing. I get number one, this quantity, times so if I'm distributing here, times xk plus 1 minus x bar, plus the same quantity, but now times x bar minus xk, right? Times the stuff from here. And then we're subtracting similar things, subtracting this. And also subtracting that guy here. All right, so where are we now? So now we see that there is xk plus 1 minus x bar here, xk plus 1 minus x bar here, so I can combine the first term and the last term to get this. This term comes with a plus sign, right? And the last term comes with a minus sign. So and this difference now multiplies xk plus 1 minus x bar plus, and then there are two terms with x bar minus xk, so I'll do a similar combination. This one with plus, and the other one with minus. Okay, so now we need to evaluate how large this thing can be. Well, so xk plus 1 minus x bar certainly is greater than 0, right? Because xk plus 1 is always to the right of x bar. So this is greater than 0. And this term is also greater than 0. So let me just do it like this. This is positive, and that is positive. Furthermore, what about these differences? How large can they be? Well, so what is the difference between capital M and lowercase m, right? Capital M is a supremum of your function f on the interval from xk to xk plus 1, and little m is an infimum of the same function on the same interval. Well, so I know that my function is bounded, right? Let's write that down. Since f is bounded, on AB, there exists now we cannot use capital M, so let's say there exists a B greater than 0 such that f of x, or absolute value f of x, right, because the function is bounded, so it's bounded both from above and below, such that absolute value of f of x is going to be less or equal than b for all x that belong to the interval from a to b, right? And so writing this is the same thing as saying f of x is between minus b and b, again, for all x between a and b. Okay. All right, so I'm trying to estimate how large this quantity can be here. And so now let's, again, think about capital M and little m. On any subinterval, capital M is a supremum, and little m is the infimum. But if my function f of x is always less or equal than b and greater or equal than minus b, that means that the supremum over any subinterval is going to be, or rather, let's put it here. Supremum over any subinterval is going to be less than capital B, and the infimum must be greater than minus b, right? Because my function is bounded by minus b from below, so infimum is bigger than minus b, supremum is less than b. So that means that capital M of f xi, actually, xi plus 1, doesn't matter how I call this, on any subinterval whatsoever, is going to be less or equal than capital B, and little m over any subinterval xi plus 1, doesn't really matter how I label it, any interval, whatever. This is going to be greater or equal than minus b for any subinterval. xi plus 1 of AB. But then from this, I can also immediately get that if I subtract little m from capital M on a given subinterval, what am I going to get? I'm going to get capital M less than b, minus little m is less than b, so capital M minus little m, possible variation of your function between maximum and minimum on a given interval, this will be bounded by 2b, right? And this is again for any possible subinterval, regardless if we're talking about the partitions P and Q that I'm looking at here, or any other subinterval or any other partition. Okay, so if that is the case for any subinterval, and I'm looking again at the stuff that I got here, what do I see? I see that this must be less or equal than 2b. And this difference must be less or equal than 2b. So if I take the absolute value of the whole thing, right, the difference should be less or equal than 4b. 4b times, right, it's certainly less than that, but nevertheless, if I have something which is less than 2b, I'm subtracting something else which is less than 2b, then the whole thing must be less than 4b. Times the length of the interval from xk plus 1 to x bar. And the same thing down here, 2b less than 2b, and again less of a length of the interval from x bar to xk. So therefore, if I go back up here, so hence the difference that I'm trying to estimate is going to be less or equal than 4b times the length of the interval from x bar to xk plus 1 plus another 4b times the length of the interval from x k to x bar. Okay? And then there is one more thing that I am going to do here. And that is going to be the following. So now, let's define the following quantity. Mesh of Q to be the maximum overall I of lengths xi plus 1 minus xi. So mesh of Q is simply the length of the largest interval in a partition Q. And having defined that, we can now express this bound above in a slightly different way. So then, so I'm looking at the same bound. So what do I see here? I see xk plus 1 minus x bar, right? That's the length of the interval in Q, in the partition Q, from k plus 1 to x bar. This is the length of the interval in partition Q from x bar to xk. All those must be smaller than the mesh of Q, right? So then the whole thing must be less than 4b times mesh of Q from here, and plus another 4b times mesh of Q from here. And if I combine these two statements, this is 8b times mesh of Q. So we have that plus another way, one more thing that we can say here. This is 4b times xk plus 1 minus x bar plus x bar minus xk. X bar goes away, and this is 4b times xk plus 1 minus xk. And xk plus 1 minus xk is an interval, one of the intervals in the partition P, right? Because Q had one fewer interval than P. And in fact, because Q is a refinement of P, right, then that means that actually if I write this, if this is the length of the interval in P, right, it must be less or equal than the mesh of P. So I can express the same statement in a different way by using a mesh of P. So also, same inequality. This difference is less or equal than 4b, right? And because that is a length of one interval in P, so it's less than mesh of P. All right, so that means that as I'm refining my partition, then the length of the interval can only, as I refining my partition, the difference between upper and lower Darboux sums for a partition is going to go down by the amount which is smaller than this 4b times mesh of p. And we will need that next time as I already mentioned, to demonstrate the second criterion of integrability.